Right, we are going to continue with a little more mathematical preliminaries, especially with regard to vector analysis, because this is going to be the sort of basic language in which mechanics is going to be studied, and therefore it's worth understanding these very clearly. I'm going to complete a couple of things which I started talking about the last time and which we had not gone to the end of. And the first of these had to do with resolving a vector, a given vector B, along some specific given vector A. So the question was, given two vectors in three-dimensional space, what is the way in which you can resolve this vector B into a component along the vector A and a component in a plane perpendicular to the vector A? And the answer was that you could write B as B parallel plus B perpendicular, and this was along A, and this component is normal to A. And B parallel we had a very simple formula for, and this formula was simply to take the component of B along A, multiply it by A, and ensure that these are unit vectors by dividing by A squared. So that's B parallel. The question is, what's B perpendicular? And the best we could do at that stage was to write this as B minus B dot A divided by A squared. So this part is B parallel, and this part is by definition B perpendicular. This was just an identity, but now that we know what the triple cross product does, this can be written down in a slightly more simple form, and that is the following. B perpendicular is moving the A squared to the top and writing it as A dot A. We have A dot A B minus A dot B A divided by A squared, taking this common factor out. And of course you recognize the fact that because we had a formula for the triple cross product which we derived the last time, you could also write this as A cross B cross A divided by A squared. So we have a very elegant formula for resolving a given vector B in the form of this nice little formula, A dot B A over A squared plus A cross B cross A over A squared. So the dot product appears in the parallel part, and the cross product, the triple cross product, appears in the normal part here. So that's a useful formula to remember, not necessary to memorize it. You can actually derive it whenever you need. It's quite easy and straightforward to do so, but it's a very simple looking formula out here. So I thought I'd mention this just so that you know what the resolution of a vector along some other direction means. This part is sometimes called the longitudinal component along A, and this is the transverse component in a plane perpendicular to A. Okay. Having done this, the next thing I want to mention is an important formula in vector analysis, which is called the finite vector formula, the finite rotation formula. And it goes as follows. I've already mentioned several times that if you give a coordinate system O with x, y, and z axis, and we rotate this coordinate system to produce another orthogonal coordinate system, new Cartesian axes x prime, y prime, z prime, such that any position vector r, which was originally x, y, z in Cartesian components, goes under this rotation about the origin. So rotation about O, it goes to a point r prime or new coordinates r prime, which are given by x prime, y prime, z prime, where x, y, z determine what x prime, y prime, z prime are according to the action of some 3 by 3 matrix called the rotation matrix. So in symbols we said that R prime was equal to a rotation matrix defined by the axis of rotation. So whatever direction of rotation you had in space to rotate about, and then in the plane perpendicular to this n, the rotation was by some angle psi. So the rotation is parametrized, as we say, is described or specified by specifying the unit vector which tells you the direction or axis of rotation and the amount by which you rotate, which is this angle psi. This matrix, when it acts on R written as a column vector, produces the new coordinates out here. In general, this is hard to write down. It's quite a messy thing to write down. But it turns out that you can actually write down a simple formula called the finite rotation formula, which summarizes the effect of this R, of this rotation matrix, on any given point R, and therefore on any vector which you start with. And it tells you how a vector transforms under a finite rotation about some specified axis n through an angle psi. And here's the formula. So R goes to R prime, any R goes to R prime, any point coordinates R go to R prime, which is R specified by n and psi acting on R, equal to. Now what can it possibly be equal to? Well, we know that the origin is left unchanged. So if R is 0, namely the components of R are 0, 0 and 0, then R prime must also be 0. A rotation is a linear transformation. So each term in the right hand side must be proportional to the first power of R, cannot depend on R squared, for instance, or any more nonlinear function of R. It must depend on n, and it must depend on psi. But you see, if you have an arbitrary vector R and some arbitrary direction n in space, these two in general, these two vectors would specify part of a triad. There is a third vector which comes out of the plane of n and R, and that is the vector R cross n, which might perhaps come out in this fashion. Now together the vectors n, R and R cross n would actually determine a kind of basis in 3-dimensional space. So this vector is R cross n and is normal to the plane formed by the vectors R and n. So it's clear that this R prime, being a vector in 3-dimensional space, must have a portion which is along R, a portion which is along n, and a portion which is along R cross n, and there is nothing else possible. So there must be something here multiplying R plus something here multiplying n plus something here multiplying R cross n. Now what goes in here is what we have to determine by this simple physical argument. Now one can derive this formula rigorously, completely from ab initio, starting systematically from the start, specifying this rotation as a proper 3 by 3 matrix. But what I am trying to give is a simple physical argument which practically enables you to guess the answer inside here based on just physical reasoning. Now this term here, I have already said, should depend on R, should be linear in R, but the vector must point along n. So it is clear that this is the component of R along n, and therefore whatever is here must be of the form R dot n times n. This is a scalar product and it is proportional to the magnitude of R, which enables us to satisfy this requirement that every term on the right hand side must be linear in R. In other words, if you multiply little r by 6, the whole answer must get multiplied by 6. Each term must get multiplied by 6. Now what can be inside here? Cannot depend on r, cannot depend on n, because this vector n, all its dependence has already been explicitly stated. So all it can depend on is this angle psi. So there must be some function of this angle f of psi plus some other function of psi, g of psi, plus some other function of psi, h of psi. And that's what the finite formula must look like, the rotation formula must look like for any arbitrary r here. Now what is it that we can say further? Well, we can simplify things a little bit by pointing out that if it should so happen that r is along n itself or n is along r itself, so looking at all those points which are along the axis of rotation, it is quite clear that these points on the axis of rotation don't get affected at all. So if I have a point along the axis of rotation, those points don't get changed at all. So r prime must be equal to r in that case. And what does that imply? Well, r cross n is 0 if r is parallel to n, because the sign of the angle between them vanishes. The angle vanishes. So this term goes away. R dot n is simply r itself. So in the case, in the special case, when r is along n, you must have r prime equal to r, must be equal to f of psi r plus g of psi r dot n, which is the same as the magnitude r, multiplied by n, which is the same as vector r, equal to f of psi plus g of psi times r. And therefore this combination must be equal to 1. So in the general case, whatever happens, these two functions must be such that they add up to unity. So we can write down, we can eliminate one of them and simply write the finite formula as plus 1 minus f of psi times that. That's already got rid of one of the unknown functions. We have just two unknown functions now. What else can we do? Well, when you have no rotation at all, it's clear r prime must be identically equal to r for every point r. And therefore, if you have no rotation at all, f of 0 plus 1 minus f of 0, well, in this case psi is 0, so 1 minus f of 0 r dot n plus h of 0 r cross n, in this case, must be equal to r itself, no matter what n is. And what does that tell you? It's very clear that it immediately implies certain things about f and h. For instance, if you have no rotation at all and I'm sitting here and that's it, no rotation at all, then r prime is identically equal to r. Or if I rotate through 0 angle, it's the same thing as saying I rotate through 0 angle. You have f of 0 here, you have h of 0, and it's trivial to see that h of 0 must be 0, f of 0 must be equal to unity. Okay. So those are little inputs which one can put in, and let's f of 0 equal to 1, h of, so that this term vanishes, h of 0 equal to 0. Okay. And then you can use further symmetry properties, such as the fact that this must change sign when psi changes from plus psi to minus psi. Well, you can also ask, can I impose the condition r prime squared equal to r squared? So dot this with itself, and then use the fact that under a rotation the distance from the origin to any point doesn't change at all. So you have to put this in as well, and this enables us to practically guess the answer. I'm going to write the answer down and tell you exactly what this looks like. This turns out to be cosine psi times r plus 1 minus cosine psi times this quantity plus, as you might guess by now, sine psi times r cross n. This is called the finite rotation formula. It's a very compact and simple expression telling you how under an arbitrary rotation about the axis n through an angle psi, the coordinates of any point, the position vector of any point transforms to some new value which is given by this formula here. 3 terms, one proportional to r, one proportional to n, one along the direction of r cross n here. Now of course we know that a vector is a set of 3 quantities in 3 dimensions which transforms precisely the way the coordinates transform. So if A is any vector, then under a rotation of the coordinate axes, the new components of A are related to the old components of A by precisely this formula. A goes to A prime, which is equal to cos psi times A plus 1 minus cos psi times A dot n along n plus sine psi times A cross n. You're guaranteed that by the very definition of the word of the vector. What's meant by a vector? A very useful and extremely practical formula, a very compact one which enables you to short circuit. You don't have to go through detailed arguments to find out what the new vectors are, new components are. You can use this formula. Now once you have this, then many other things are possible. If this is a position coordinate, then I can ask what happens to the velocity, what happens to the acceleration and so on under a rotation of the coordinate system. In particular, and we will do this subsequently, one can ask, if I go on rotating about this axis n at a constant angular speed omega, then this psi increases with time like omega t. It's just starting from 0, it is equal to omega t, increases with time. So I put that in here, and then you see that the new coordinates are changing with time. Now if you have this as the position of a particle in the original coordinate system, one can now predict what it will do in a rotating coordinate system. And then one can look at what the acceleration does and so on, and we will subsequently see that the whole idea of inertial forces or non-inertial forces or pseudo forces emerges from this formula here in a straightforward way. Meanwhile, before we do that, let me just point out that this formula reduces in the special case when you had a rotation in the z-axis, along the z-axis. So now I'm going to look at this situation, x, y and z. That was the origin, and I'm going to look at a rotation along the z-axis itself. So that's the unit vector n, which is equal to the unit vector in the z direction, and ask what happens to this formula. Well, it's immediately clear that we expect nothing along the z coordinate to change. So the z coordinate, the vertical coordinate of no particle should change at all, and the x and y coordinates should get mixed up according to rotation in a plane, and for that we already have formulas. So is this true? Is this coming out? And the answer is yes, because if n equal to az, then let's look at what the new coordinates are, and let's look at the x component of it. So this is equal to x prime, and that must be equal to the x component of r, which is x itself, x cos psi, plus 1 minus cos psi r. Now we are looking at the x component, so this is proportional to ex, dotted with n, ez is 0, plus sine psi, that comes in, plus sine psi, and then you're looking at the x component, ex crossed with ez out here goes to ey with a minus sign. On the other hand, the ey crossed with ez is going to give you ex. So can we do that? The y component here crossed with Ez gives you Ex. So I am using the fact that Ey, so the y component of this R is of course y, and then there is a sin psi, and that is it. Okay. On the other hand, the y prime component will have the y prime component here, so this is y cos psi. I have written this out. Ey dot Ez is 0 once again, and then Ey cross n is going to give me so it's the x component that's going to give me a y, and therefore this is minus and there is no z here, there is no z here. And what about z prime? Again z cos psi plus this is z Ez dot Ez, Ez dot Ez is 1, and then z times n out there, that gives me z itself, and then Ez cross Ez is 0, so that does not contribute at all, and this is equal to z. So this checks out. It essentially tells us that if you rotate about the z axis, points, the z coordinate of points do not change, and the x and y coordinates get mixed up according to this plane trigonometric formula. So the general formula reduces to this special case in the case that we have looked at earlier from simple geometry, but this is the general formula here, a very useful one, and we will have occasion to come back to this subsequently. All right, the next topic now is to look at polar coordinates in 3 dimensions. Again, a topic of great importance, so let us look at polar coordinates in 3 dimensions. And just to refresh your memory, we looked at plane polar coordinates in the xy plane with the origin here, and the statement was if you gave me an arbitrary point there with coordinates x and y in Cartesian coordinates, I could look at it in terms of the distance from the origin, which I call rho, and the azimuthal angle phi, the angle made from the x-axis to this radius vector, and we had the radius vector of any point was rho times E rho, the unit vector in the direction of increasing rho, and we had an orthogonal vector in the direction of increasing phi. So we had that thing there, and the unit vector E rho was equal to cos psi times Ex plus sin psi times Ey, whereas the vector E phi was equal to minus sin psi Ex plus cos psi E rho. We also know that E rho dot E phi equal to 0. They are perpendicular to each other at every point. We saw at some length that E rho is a function of psi, of the position of the azimuthal angle of the point, as is E phi according to these formulas here. Sorry, this is E rho, Ey. Ex and Ey are the same at all points. So that's Ex, that's Ey, and it remains the same wherever you are in the plane. So this much we had already seen from plane polar coordinates. What also remained was that in the infinite plane, the ranges are 0 less than equal to rho less than infinity, and phi 0 less than equal to phi less than 2 pi, in order to make phi single valued, because 0 was identified with 2 pi. Okay. one little point got left out, and that is the distance between 2 points. So if you had 2 points next to each other, a point here and a point here, and asked what's the square of this distance, in Cartesian coordinates this is very simple. So if I call this distance ds, that's dx and dy, so it's immediately clear that ds squared by the Pythagoras theorem is dx squared plus dy whole squared. But if you want to do it in terms of plane polar coordinates, you have to argue slightly differently. That's the rho for one point, that's the rho for the other point, the neighboring point. There's a change in angle which is of the order of d phi, okay, which is d phi here, and this distance, if this is rho, then you again do exactly the same thing as before. You draw a circle of this kind of radius rho, then the reason there's a line element, this thing here, is the square of this quantity is what we want to find. It's equal to the sum of this square plus this square. But the sum of this square here is purely due to the increase of rho. So that's d rho. On the other hand, this quantity here is rho times d phi, whereas that portion is d rho. So therefore, the square of the line element can also be written as d rho squared plus rho squared d phi squared in plane polar coordinates. The square of an infinitesimal ds squared is given by these two quantities, and dimensionally you can see this is all right because this is length and length squared, length squared, length squared, length squared, dimensionless quantity here. It's important to recognize that there is a coordinate dependence in the line element here as soon as you go to any coordinate system other than Cartesian coordinates. This is absolutely crucial. Now, the extension of this to a third dimension can be done in many ways, but the most trivial extension is to simply say the z coordinate is not affected at all. So what one does is to introduce the cylindrical polar coordinates here. And now you do exactly what you did earlier for plane polar coordinates. So this is the xy plane on which you use plane polar coordinates, and if you have an arbitrary point here with a radius vector r in 3 dimensions, then the cylindrical polar coordinates would correspond to drawing a projection of this onto the xy plane here. That distance is rho as before. This angle from the x-axis is the azimuthal angle phi as before, and the third coordinate is this height here, which is the same as this height here, and this is z. So the position vector of any point is described in cylindrical coordinates by rho, phi and z, this triad of quantities. The ranges of rho and phi are exactly as over here, and 0, minus infinity, less than z, less than infinity. Z positive is above the xy plane, z negative is below the xy plane in this fashion. So the connection to plane polar coordinates, the Cartesian coordinates is obvious. It's exactly as it is in plane polar coordinates in the sense that x is rho cos phi, y equal to rho sin phi, and of course z in Cartesian is the same as z in cylindrical polar coordinates in this fashion. What's the line element now? That's all that remains. The line element is the square of 2 points. So you can see by the Pythagoras theorem that r squared is rho squared plus z squared. So you see that r squared is rho squared plus z squared, and rho squared is x squared plus y squared, of course. So the geometry is extremely straightforward. The square of the line element is ds squared equal to d rho squared plus rho squared d phi squared plus dz squared, this fashion. The unit vectors are interesting, and this is what we will look at next.